In this lesson, we're going to cover the first part of 8.1, and we are talking about kinetics. So first, we'll start with some definitions. What is kinetics? Kinetics is just the study of the rates of reaction. So we're going to be looking at the rates of reaction, how quickly or how slowly a reaction occurs. We're also going to talk about factors that affect the rate of reaction. So if we want a reaction to speed up or slow down, how can we do that? Let's define reaction rate. Reaction rate is just the speed at which a chemical reaction occurs. The speed at which a chemical reaction occurs. When we are talking about if a reaction can occur and how quickly it can occur, it is going to depend on something called collision theory. Collision theory. Collision theory states the rate of reaction depends on how often particles collide. And with how much energy. The rate of reaction depends on how often particles collide and with how much energy. Let's say I had reactant A and reactant B, and I wanted them to form compound AB. Well, if A never collides with B, they're not going to be able to form compound AB. The more collisions and the faster those collisions occur, the quicker we can make product, the faster that reaction is going to be. So, two important parts to collision theory, and then I'll draw out an example. Collision theory depends on how much energy those particles collide with. The activation energy is the minimum energy required for a reaction to occur. So the way that I always think about activation energy is pretend this is the potential energy diagram. We will talk about these later. So pretend right here you had a golf ball and we wanted to swing our club and we wanted to hit the golf ball so it goes up and over the hill. Well, let's say you only swung that club with a little bit of energy. Well, what's that ball going to do? It's going to start to roll up, and then it's going to roll back down. If we don't hit that golf ball with enough energy to go up and over the hill, it's not going to get to the other side. Activation energy for a chemical reaction works the same way. This would represent my activation energy. If you don't put enough energy in, that reaction is not going to occur. The second part of collision theory is called the orientation factor. Particles have to be orientated in the correct position. Collisions don't always end up in a chemical reaction. Collisions between molecules result in a reaction only if the molecules are oriented in a certain way when they collide. So, what do we mean by that? Let's say I had substance A and I had some molecule B, C. A collides with B. To make molecule AB. Let's say our molecules weren't oriented in this way. So now, let's say A was to collide with C. Well, here we would say no reaction. If we are trying to produce compound AB, A needs to collide with B. So if they don't collide in the correct orientation to where we can form that product, or if they don't collide with enough energy, that reaction may not occur. Let's talk about the factors, and there's 5 of them. These are going to be our factors that affect reaction rate. Number 1, concentration. The trend for concentration is direct. Increasing the concentration increases the reaction rate. I call this a direct relationship because they're both going up. As concentration goes up, reaction rate goes up as well. Well, why does this occur? Why would increasing the concentration increase the reaction rate? Because there are more reactant molecules available to collide and react. Let's look at a picture. So let's say I had some reactant molecules, but now I am going to increase the concentration. So maybe I double it. Which one of these beakers would have more collisions? Pretend I was better at drawing and this was drawn to scale and we had the exact same volume. So if the volume of the container stays the same but the concentration goes up, The more molecules you have, the more collisions you're going to have. Compare our hallways. When we are face-to-face with 3,300 students, you're going to run into someone in that hallway because there are a ton of people, compared to our hybrid hallways where you might not see anyone. You're less likely to collide with someone. The more people you have, the more collisions there are. The more molecules we have, the more collisions we're going to have as well. So first factor is concentration, direct relationship. As concentration increases, reaction rate increases as well. Factor number 2. Temperature. Again, direct relationship. Increasing temperature increases the rate of reaction. Why? So we're going to talk about temperature much more in the next unit. Unit 9 is thermochemistry, so we talk a lot about heat and temperature and what that means. But when we're talking about temperature, temperature is a measure of kinetic energy. Kinetic energy is the energy of motion. So as temperature increases, molecules move faster. As temperature increases, molecules move faster. Well, why will that increase the rate of reaction? Remember, it all comes down to the collisions. We need to have more collisions, and we need to have them happen with enough energy in order for that reaction rate to increase. So as temperature increases, molecules move faster and are more likely to collide with enough energy to react. If we have some faster moving molecules, we're going to have collisions with greater energy, more chances to reach that activation energy, meaning we're more likely to have a successful collision. Factor number 3, surface area. Again, direct relationship. That makes remembering these really easy. Surface area. The trend is that increasing the surface area increases the rate of reaction. Why? Well, if you increase the surface area, there are more places for collisions to occur. So let's say we had like a cube, and we want our molecule to collide with it. So maybe we have like a piece of metal, and it's like shaped like a cube. Well, only these molecules that are on the perimeter are able to have collisions. So let's say we now take that piece of metal or that compound or whatever it is, and we were to increase the surface area. So before, the only area that we could have collisions were around the perimeter. All of those molecules or atoms on the inside are isolated. Now we take this piece of metal or this compound and we crush it up into a bunch of smaller pieces. Look at how much more surface area we have. We have all of this extra space to have collisions. The more space we have for collisions, the more collisions we can have. The more collisions we have, the faster the reaction can occur. All right, 5 factors, 2 to go. We can also change the rate of reaction by altering the pressure or volume. And again, it is a direct relationship when talking about pressure. Increasing the pressure increases the rate of reaction. Why? I think it's easier to describe this in terms of volume. And what we have to know is that volume and pressure are inversely related. So increasing pressure decreases volume. If we decrease volume, we're going to have less space. So now, molecules have less space to move, which means they're more likely to collide. We'll draw a picture for this one as well. All right, so we have our molecules. They're in some type of container. And let's say we increase the pressure. If we increase the pressure, you are decreasing the volume. So now the volume is much smaller. But we didn't change the concentration. Concentration stays the same. So which box is going to have more collisions? Well, the one that's much smaller. Less space to move, more collisions we have, the faster that reaction is going to occur. So we get increased concentration, increased temperature, increased surface area, increased pressure. Last one is we can add a catalyst. So a catalyst, its whole function is that it increases reaction rate. These are agents that increase the reaction rate without being consumed or being used up. So an important thing to note about the catalyst is it doesn't change the reaction. You have reactant A plus B, we're making product AB. Adding a catalyst doesn't affect the reaction. It doesn't make new products. It doesn't get consumed by the reaction. It just makes the reaction go quicker. Well, how does that do that? It provides an alternate way for the reaction to occur with less activation energy. Provides an alternate way for the reaction to occur with less activation energy. Let's say you had an acre of land and you needed to mow the grass. You could do it with a push mower. That's going to take a whole bunch of energy to push that lawnmower around, and it is going to take you a very long time to mow an acre of grass. Let's say we found an alternate way to get that grass cut, like a riding lawnmower. Well, that's going to take less energy, and you're going to be able to complete that job quicker. That's kind of what a catalyst does. It provides a new way for the reaction to occur with less energy. The less energy that needs to be put in, the faster the reaction can occur.